9, they do give us a formula to use here, and I'm going to derive that formula in a minute. I want to take you through a strategy that I think works well with stuff you know from geometry and Algebra 1 to get the answer to this problem. And what I'm going to do is set up a proportion. So I've got a radius of 15 inches. I've got an arc length of 8 inches. So if I lay a piece of string across here, even though it's curved, that would be 8 inches long. And I'm trying to find this angle right here. So again, I'm going to set up a proportion. And what I do know is that this length, 8 inches, is a portion of the entire circumference, which is 30 pi. And I know that because circumference is twice the radius or diameter, and then times pi. So 2 pi r, or diameter times pi. And now that I've got a proportion of this piece to the whole circumference, I'm going to do the same thing with the angle. So this 8-inch arc comes from this 8-inch arc comes from this angle, which is a piece of the whole circle. Now I want to keep this in radians because I've got pi involved. So the whole circle is 2 pi radians. So one more time, an 8-inch section of the entire circumference, and this angle out of the entire 2 pi radians. That's my proportion. Before I begin, I probably should go ahead and put inches right here because circumference is also in inches, and really that goes away immediately, so we don't really need to worry about that. 2 times 8 is 16 times pi. This one's 30 pi times theta. So divide by 30 pi. And reduce, I'm going to get 8 over 15 as my angle. And that is in radians. So I'll put a little, because it's 8/15ths of the radius. And another way to kind of look at that, a radian is the radius stretched across the edge of the circle. 1 radian would be 15. This is 8 out of 15 inches for 1 whole radian, so hopefully it kind of makes sense that way. Now the book gives you this formula, r or theta equals s times r. So let's talk about how they get that. Let's do the same thing, but this time let's do it with symbols only. So I've got r, I've got an arc length, which we're calling s here, and then I've got theta as my angle. So we'll set up the same proportions. What I do know is that s, this arc length, is out of the full circumference, so 2 pi r, is that circumference formula. And I know that this angle right here is out of the full 2 pi radians. So I'm just doing everything I did with actual numbers, I'm just using symbols this time. So 2 pi times s for arc length is equal to 2 pi times r times theta. And if I divide that 2 pi out to get s by itself, then I get the formula that the arc length equals radius times theta. So there it is, kind of proved. And hopefully it kind of makes sense intuitively, because if a radius, or a radian, is the radius stretched across the edge of a circle, then your arc length is your radius length times however many radians that you go through. So there's several ways to think about it. Hopefully something sticks that can help you get through that. All right, 109, we've got a saw blade. I couldn't find a good picture of a saw blade, so I just put a circle in here. But we've got a diameter of 7.5 inches, which I'm going to go ahead and do the radius here. Radius will be 3.75 inches, because most things involving radians involve the radius. It's going to spin at 2,500 RPMs. Now, RPMs are rounds per minute or revolutions per minute. So how many times it goes in a full circle in 1 minute. First up, we're trying to find the angular speed. So I'm going to do a little unit conversion chart, kind of like you do in chemistry. And I'm going to begin with the speed that we have, 2,400. I'm going to go with the words revolutions per minute, rounds per minute, revolution. It really doesn't matter. What's important is that 1 revolution or 1 round, one time around the circle is, and we're going for angular speed here. If I was going for linear speed, I'd probably go for an actual measurement. How many inches is it around the circle? Since I'm going for an angular speed here, I want to know I want to know what the angle is all the way around the circle. So 1 revolution, that's 2 pi radians. So I'm going to say 2 pi radians. It gets rid of my revolutions. And I'm trying to go to seconds. Right now I'm in minutes. So right now I'm in radians per minute. I want radians per second because that's what the book tells me I want to end up with. So 1 minute has 60 seconds in it. So now the minutes will go away. So you multiply all that out, and it comes out to be 80 pi radians per second. For linear speed, I'm looking at how many inches this thing moves in 1 second. And I think they actually want feet per second, so we'll have to get to that conversion. But it's a distance that it actually covers. If this thing was able to, if it was like a tire and it was on the ground just going, that's how many feet it would cover in that 1 second's time. Your angular speed is how much rotation does it go through in that time. So that's the difference. Where angular is just how many times the radius does it go around in a second or minute or whatever. And like in linear, it's just if it was driving on the ground, how much distance would it cover? How much actual circumference distance does it cover? It tells me I want to end up in feet per second. So I'm going to begin with what I know the radius is. 1 radius, or radian, either way, they're the same distance, is 3.75 inches. All right, so radians is gone out in inches per second, but they asked me to do feet per second. So there are 12 inches per 1 foot. So that makes inches go away. And now we'll be in feet per second. And if you multiply it out and leave the pi, it's 25 pi feet per second.